Hi, Math 3 students. Today we are going to review complex numbers. So last year in Math 2, you guys learned about imaginary numbers. Imaginary numbers occur when you take the square root of -1, all right? So the square root of -1 is equal to I, all right? So kind of the two things you have to commit to memory here are that the square root of -1 is I, and that I squared is equal to -1. And that makes sense because you think about like when you square something inside of the radical, whatever's inside of the radical pops out, okay? So something like this here, you would break this down into like -1 times 9, all right? The square root of 9 is 3, so that comes out as a 3, and the square root of -1 is I, so that comes out as an I. All right, here we break this down into -1 times 5. All right, you cannot take the square root of 5, so that can't come out of the radical. But you can't take the square root of -1 if we're dealing with imaginary numbers. So we end up with I root 5. Then here we should end up with, we break this down into -1 times 16. 16 comes out as a 4. -1 comes out as an I. We get 4I. The I should always come second whenever you're like writing the it with the coefficient, right? It's kind of like 4x, right? You wouldn't write it as x4. Same thing with I. You would write it as like 4I. All right, and then so for breaking down radicals, before we had a 5, and you can't really simplify 5. But when you have radicals like this, you have to break it down into the biggest perfect square that you can. Perfect squares are numbers like 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and so on. How did I get all of these numbers? I just did 2 squared, 3 squared, 4 squared, 5 squared, and so on. All right? And all of these numbers you can take the square root of. You get 2, 3, 4, 5, 6, and so on. So you got to figure out what's the biggest number, biggest perfect square that's going to go into 72. All right? So one way to kind of do that is to like just look at all the numbers less than all the perfect squares less than 72 and find the biggest one that divides into it. And in that case, it's going to be 36. So how we're going to break this down is we're going to take out our -1, all right? And then 72 becomes 36 times 2. Now, again, I broke it down into 36 times 2 because 36 is the biggest perfect square that goes into 72. There are other perfect squares that go into it. 4 goes into it. 16 goes into it. However, again, the goal is to find the biggest one, or else it's kind of like GCF, right, where if you don't take out the biggest thing, it's not fully simplified. So we go ahead. The square root of -1 is I. Square root of 36 is 6, and then the 2 stays on the inside. All right. So complex numbers are written in the form A plus BI, where A is the real number and BI is the imaginary unit. So when you're adding and subtracting, you essentially just treat imaginary numbers like variables. The only time that things are going to get wonky is when the i's have powers on them, because then you can simplify them. But other than that, if it's just a plain old I, you just treat it like an x. So we're just combining like terms here, all right? These guys are going to come together and we get, what, -7? These guys come together and we get a positive 2i. And again, remember you put the real part and then the imaginary part. Here, this is subtraction. So if you think about how we subtract polynomials, remember you distribute. So we get a -2 and a plus 5i. We combine our like terms. We get 4 plus 13i. Next one, these guys come together, we get a -6. These guys come together, and we get a -3i. You could, I know some of you guys like to like distribute the positive, that's fine. When you distribute a positive, everything just stays the same, right? So you get a -2 and a -9i, which again just gives you what we had. So when I have a positive, I just treat it like combining like terms. And again, when you have a negative, you got to distribute it. So my first guy stays the same. I distribute the negative, I get a +4 and a -i. Combine my like terms, 7, like terms, -3i. And again, remember the real part comes first, then the imaginary part, okay? So now we're going to go ahead and find products. Now, if you recall, when you combine like terms, the powers on things don't change. But when you multiply things with like variables, the powers are going to change, right? And what's important about this for imaginary numbers is that I squared, whenever we have an I squared, we have to replace that with a -1 and then simplify from there, okay? So what's going to happen here is I distribute, and I get -16i plus 18i squared. Now, this I squared is going to be replaced with a -1. So now I have -16i plus 18 times -1. 18 times -1 is -18. And if you recall, we write our complex numbers, that's numbers with real and imaginary parts, with the real part first. So we should write this as -18 minus 16i. All right, and then something like this. This is going to be like a FOIL problem, right? You got to distribute. So we get 9 plus 6i minus 6i minus 4i squared. All right, so there's a lot going on here. 6i and -6i cancel out. So I've got the 9 out in front. And then my I squared, I have to replace with a -1. All right, so -4 times -1 is going to give me a +4. And now my answer here, or I should say the result here, is just all real numbers. So you just combine like terms and you end up with a 13 there. All right, so the i's actually all went away. All right, same thing here. We distribute this guy. We get 20i minus 10i squared. We got to replace our I squared with a -1. We get 20i plus 10, and then of course we write it with our real part first. So 10 plus 20i. All right, and then here we distribute. We get 1 minus 2i plus 2i minus 4i squared. These guys cancel. Now, you're probably like, well, why? How come all of these terms are canceling? And we're going to talk about these guys. You see how it's like the real number part's the same, but the imaginary number part is like opposites of each other? These are called complex conjugates. And when you multiply complex conjugates, what ends up happening is the imaginary part kind of goes away. So we'll talk about that again in another lesson. So we replace our I squared with -1. We've got 1 plus 4, which is going to give us a 5.